Next, we need to talk about the stress on a fluid. Remember that fluids are elastic and viscous, and we can approximate them as a deforming elastic body, and it resists these deformations through these viscous forces. This particular elasticity on the fluid motion, we might see that these deformations are inducing forces and vice versa. We'll assume that there's a small delta V, which represents the fluid parcel, which is very small. The deformation induces a force exited on the surface of the fluid parcel. This resultant force, which we'll call capital F vector viscous, will be given through a tensor, math script T, and we'll call this the viscous stress tensor with the pressure. We'll define this viscous force as this integration of the surface stress with the velocity over the fluid surface in equation 90. We can also write this just with an explicit summation or index notation, but the summation is not required. We'll use Green's or Odrogorski's formula, and it'll yield a particular force density for the stress, which we can write as a little f in direction I. The summations implied or written explicitly from j equals 1 to 3 in 3 dimensions of the partial j of the stress tensor. This can be written as the divergence of Ti. George Gabriel Stokes showed that the relation between the stress tensor and the strain tensor is linear for small velocities and the particular derivatives of the velocities. And the fluid's isotropic, not the statistics of turbulence, if you will, but the statistics are invariant with respect to the viscous terms, we'll find that the viscous force is the sum of the second derivatives of u, which is an important observation by George Gabriel Stokes. For an isotropic fluid, the change in referential through a rotation will not alter the relation between the force and velocity. Using this assumption, this means that the viscous force is determined only by the particular viscosity coefficients. And in this case, in the classic Navier-Stokes equations, there's two. Professor Richard Feynman says that the most general form of the second derivatives that can occur in a vector equation is the sum of a term in the Laplacian and a term in the gradient of the divergence. And indeed, that's what we see in the Navier-Stokes equations. George Gabriel Stokes argued that the force density associated with a stress of an isotropic fluid for small particular velocities is equation 93, which is a boxed equation. It'll be mu of u plus the second coefficient of viscosity of the divergence of velocity. It's easy to see the correspondence between this particular equation 93 and the relationship of our stress tensor with epsilon, where the trace of epsilon is given here and lambda is given here, which represents the second coefficient of viscosity. We'll define lambda as what we usually call viscosity. It's the first coefficient of viscosity, mu, and lambda will be the second coefficient of viscosity. So this form here is holding for Newtonian fluids, where there's a linear stress-strain relationship. George Gabriel Stokes expressed this particular internal pressure in a general way that allows for many, many, many good predictions of fluid dynamics, even used today. The so-called Stokesian fluid, the stress tensor will be related to the strain tensor in homogeneous isotropic fluids in a nonlinear way. So therefore, the Stokesian fluids will satisfy the following properties. The stress tensor is a continuous function, and the strain tensor in local thermodynamic state, but it will be dependent on other kinematical properties. T will not depend explicitly on x, that is its position in the fluid, or its rotation. The fluid will be isotropic, and there'll be no particular deformations. Then that implies that the fluid is in hydrostatic state.